Depth first search is an algorithm for traversing or searching the tree or the graph using a data structure. The states keeps reoccurring. As we told, we have reoccurred the node B twice and node A once. State keep on reoccurring. There is no guarantees of finding the solution. The depth limit search can solve the drawback of infinite path of depth first search. Hello everyone, welcome to one more session on Artificial Intelligence and Application for 6th semester BCA students. In this particular session, we are going to discuss uninformed search. We have seen what are the informed search and uninformed search. In this session, we are going to discuss uninformed search. Myself, Indu J, Faculty of Computer Science Department, Vidhyaashram First Grade College, the Temple of Excellence, MYSURU. Let us start today's session. In uninformed search, we have already know what is uninformed search. We don't have a information of searching. We have only the current information when we are going for the search algorithms. So first search algorithm in the uninformed search is a depth first search. What is a depth first search? As the name itself indicate, we are going deep in the tree, whatever the graph or the tree. Whenever we are representing a graph or the tree, each graph is converted into the tree and we are going level by level, deep into the level. We are not sorting according to the nodes, whatever the child nodes occur. We are just searching the element, going into the deep into the levels of tree. That is called as depth first search. Depth first search can be a recursive function or recursive algorithm, or it can be a non-recursive algorithm also. Either the way we can implement depth first search algorithm. Depth first search is an algorithm for traversing or searching the tree or the graph using a data structure. Which type of the data structure we are using? We are using a stack data structure, since it works on the principle of last in first out. Since we are using the last in first out strategy, we are using the stack data structure. The algorithm starts at the root node and explore as far as possible along with the each branch using before backtracking. We have used the concept of backtracking. Once we are not finding the element beneath under the tree, we have to go back to the different nodes. We can explain you when we are explaining this with an example. Okay, so keep in mind that backtracking is going back to the before node. That is called as backtracking. DFS implementation using backtracking. That's what we are exactly. So let us see the example. Here we have one graph. Which solution could be the DFS to find the move from the node S to node G? What is our starting node? S is a starting node. G is what? Our goal node. Goal node means goal what we are searching for particular node or the particular element. How we are converting this, how we are implementing depth first search using for this particular graph. This particular graph is converted in the form of tree as of to find the solution. What we have is yes, that is a start node. From start node we have A and D, two children node for S, and then A is having one child, that is B, B is having two child C and G, and C is having one child G. You can see that here B is also reaching to G, C is also reaching to D, D is also reaching to G. So here all the nodes are reaching to the goal state. But we have to find a depth first search, right? We have to implement the depth first search to reach the goal. So what exactly from the starting node, what exactly it will go to its successor. It will go to its successor. Once it will reach to the successor A, it doesn't look into the another successor. It will go in the deep of that successor. Now we are at the A position, node A position. Next it will go to the next successor of A, that is B, right? Next, what is the next successor of A? B. Then we are not searching any other element is present or not, the siblings of that node is there or not. We are just going to find the successor of B. Again we are finding the successor of B as a C, then successor of C as a G, which we are reaching to the goal state. Right, here in this example what we are giving, we are getting the goal state once we are going beneath into the tree. But take one more example where we need to go for the backtracking. So what I'll take a start node as S, A, B, C, F, G, and I. So let us take one more example where we are supposed to find the same goal state G from the start state. Yes, here we are doing the backtracking. Why we are doing the backtracking? Once we are traversing through the tree to the beneath of the leaf node till the leaf node, still we are not getting the solution or not getting the goal state. So we have to do what? Backtracking. How the backtracking has been done? Let us see. First, from the starting from the node, yes, we are going to the node A. From node A, we are going to the node B. Node B, we are going to the node D. That is the third operations what we have done. Here, we don't have further node. What we have to do? We have to go for backtracking here. We have to go back to the B. B is already visited. Where we are exactly? We are in S. From S, we have visited A. From visited B. From visited D. Right? So we have already visited B. So what it will do? It will skip the B and it will from D it will visit to E. Right? From D it will visit to E. Once again we are not getting the goal state G here. So what we have to do? Again we have to backtrack. We have to go for the B. B is already visited. So we have to go for the next node or the sibling of the B, that is C. So we are visiting to the C. C is again a leaf node. We are not getting. So we have to go back again to the node A. So node A is already visited, so we are not representing a node A in the path, so it will go to the node F. Here node F, it will go to the node F. From node F it is visiting to the node G, right? So node G. So now we are finding the goal state or goal node. Search the element which we are supposed to be searching for. This is called the backtracking. Once we are reaching to the leaf node of the tree, but we are not finding any elements, so we are going for backtracking. This is a operations, or this is a algorithm how exactly depth first search is working for. So hope clear. Main point is that it has to go till the leaf node until unless you are finding the element. If you are not finding the element when you are going deep into the leaf node, then you have to backtrack according to the algorithm. So what are the advantage and disadvantage of depth first search? Advantage of depth first search is it requires less memory. As once in a shot, if we are going down, we are getting the result. So it requires a less memory and it requires a less time for execution or reach the goal. What is the disadvantage we have? The states keeps reoccurring. As we told, we have reoccurred the node B twice and node A once. State keep on reoccurring. There is no guarantees of finding the solution. This is not an optimal algorithm. It cannot guarantee you to give a solution. Whether the searching element is present or not, it's not guaranteed. Then as it traverses deep down, searching may be enter into the infinite loop. If the tree is very large, it keep on going in till the leaf node, the searching may enter into the infinite loop, though we are not finding the proper solution. This is the main disadvantage what we have in the depth first search. This is one algorithm for searching. Then second algorithm what we have for the searching is breadth first search. What is a breadth first search? As we are depth first search, we are going deep into the tree. We are moving towards from left to right. Wide wise we are going, width wise we are going. Breadth first search is, we call it as BFS, is an algorithm for traversing or searching a tree. Here what kind of data structure we are implementing? We are implementing the queue data structure. There what we are doing? We are implementing the stack data structure, that is first in last out, but here we are using first in first out queue data structure. Starts from the tree root and explore all the neighborhood nodes that are present. It goes to the child node, then from the child node it goes to the sibling, then from the sibling to his child node, from his child node to the siblings again. It will go like this, not like this. Okay, not into the deep by using the width of the tree. Search from the root node and expand the successor node at the current level. What are the successor node? What are the siblings of that successor node will be expanded. So we are implementing what? FIFO technique to develop the algorithm of breadth first search, BFS. So let us see the example. Same graph we have from source node S, we have to reach to the G, right? That is our goal node. How we are going to do this? Using the BFS algorithm. In the BFS algorithm, traverse shallowest the node first. Whatever the successor node, that will be treated as first node, right? From here, it will traverse to the node A. From node A, it will traverse to the node D. From node D, it will traverse to the child node of the D, that is G. If it is not found here, then it will traverse to the next node, next sibling of this node G. It always pick the shallower branch unless it reaches the solution. For this particular, we are taking from S, D and G. We are finding the solution directly from S to D and D to G. This is the shortest path what we can find the solution for. Or you can take the one more example where we have done as S, A, B, C, D, E, F, G, H and I, right? Now here what we are doing, from the start we are moving to the node A as a first step. From node A we are searching for the node F. So what is the path? S goes with A and goes with F. So if you want to use that in the form of data structure, that is in the queue form, let us have first what we have to put. We have to put the stat state. From the stat state where I am reaching, I have to remove this as a queue is first in first out stack. Right, insertion will be at the rear end, deletion will be at the front end, right? Insertion, we have inserted the stat node. Once we are moving to the second level, level 1. From level 0, we are reaching to the level 1. Once we reach to the level 1, what are the child nodes of the S, that will be pushed into the queue and this will be removed from the queue. And F will be the content of the queue. Now, after finding this A and F, now what it has to do, it will go to this position, the child node of F. What is a child node of F? That is H. Now how we are putting it? Now what all the elements are there in the queue? A and F. So A is already visited, remove the A. What is F? F's child node what we have as G and H, right? G and H. Now, once we have a G and F, now we have to check for A's children node, that is G, H and B and C. We are reaching to the G, which is a goal state here. We are reaching to the G, which is a goal state. Since we have found the goal state, we are not moving further. We are not moving further for traversing the tree as we have visited the goal node. So, what would be the path here? S provides A, then F, then H and then G. So, from start node, we are reaching to the goal node using this particular path. That is called as breadth first search. So, it will implement like this. 1, 2 and 3. It will traverse all the element of the tree. So what is the advantage and disadvantage of breadth first search is BFS will provide the solution if there exists a solution. It will say it provide the solution only when it will exist the solution, and the if more than one solutions are available, it will select the minimal element. As in this example we have seen, we have more than one solution, but we are reaching to the solution which is very shortest one. So that is the advantage of breadth first search. What is the disadvantage of the breadth first search? It requires a lot of memory because each level has to be saved in the memory. As it moves like this, each node has to be saved in the memory. That's why it requires large number of memory. BFS needs a lot of time for identifying the solution, because it has to visit each and every node, right? So that's why it requires lot of memory as well as lot of time to search the particular element. So this is all about breadth first search. Next algorithm what we have, searching algorithm, is depth limit search. It is same as that of depth first search. The only thing here is we are limiting the searching. We are giving one threshold value. We should not cross that threshold value when we are when we are searching for an element. So in the depth first search, what we are doing, the depth limit search algorithm is similar to depth first search with predetermined limit. We provide one limit until unless which level have to go for searching. We are providing one threshold value. The depth limit search can solve the drawback of infinite path of depth first search. What is the disadvantage we have in a depth first search? It will go to infinite loop as tree is very large, tree grows downwards. So providing the limit, we are overcoming from that particular disadvantage. It avoids a search going into the infinite loop. Node at the depth limit will treat it as a no successor node further. Whatever the nodes are there, after that limit, if the successor nodes or the child nodes are also there, we treat it as no successor node or no child node after that particular level. The depth first search can be terminated with the two conditions of failure. When we can terminate the depth first search, first one is standard failure value. If the search is failed, we are not finding any solution for that particular searching element, that is a standard failure value. And cutoff value means we have limiting the search in that particular limited area. If the element is not found, then it will be terminated. It defines a no solution for the problem within the given depth limit. In that particular limited area, if element is not there, then it will be terminated. Okay, saying that no result found. Let us see the example for depth first search. Here, as we have a tree for the depth first search, what we have to find? This is a start node, and this is our goal node, right? This is our goal node. We have to reach from the node S to node G. As it will work as a depth first search, it will go as a first, it will go to the node A. From node A, it will go to the node C. From node C, as we are limiting the search to the level 2. What we are doing? We are providing the limit to the level 2. We are searching the element which is there till the level 2. We are not going to the level 3. Okay. So what we are doing? So from here we stop, we don't go to E and F because we have limited the search to the level 2. From here it will go to the backtracking, it will go to the D, it will go D. Once it will go D, it will go to backtrack to A because A is already visited, we are not putting A as a path. So it will go to the B. Once it will go to the B, it will go for the next depth. next depth, that is tree, and the next it will visit to j. Now if it is a j is a goal state, we are say that we can find the element at this particular path. What is a path to find the element? From S it will go to A, from A to C, from C to D, from D to B, from B to T, and T to J, right? So this is a path where we are finding the goal state, that is J. If my goal state is G, if I consider this is my goal state, so in this particular DLS, that is a depth limit search, will not provide the solution. Though element or the node present in the tree, it will say that there is a no element, though searched element. Why? Because we have limited the search till the level 2 and the goal node G is present in the level 3. So it will not give the proper solution. Though element is present, it will say that the element is not there in the tree. Understood? So that is coming back to the advantage and disadvantage of the depth limit search. Depth limit search is a memory efficient because we are storing only the limited number of nodes. How? We are by providing the limit for the searching. And the disadvantage what we have in the depth limit search is also the disadvantage of incompleteness. What is incompleteness? That's exactly what I said. If the goal node G is present in the tree also, it will say there is no element or no node called G because we have limited the search for the level 2. So that is called as incompleteness. It may not be optimal if the problem has more than one solution. When the number of nodes are reaching to the particular node G or the goal node, it won't give the optimal solution. It gives the solution randomly. Optimal solution means what? Effective solution, which is the shortest path and which consumes a short memory and a shortest time. That is called as optimal solution. It does not provide the optimal solution. Okay, major disadvantage is incompleteness and it does not have a optimal solution. These are the two major disadvantage. And what is the advantage? It is a memory efficient since we are providing the limit for the searching. The nodes whatever required to store, that will be memory efficient. So this is the advantage and disadvantage of depth limit search. So in today's session we have discussed 3 searching algorithm, that is uninformed searching algorithm. One is DFS, BFS and DLS, that is depth first search, breadth first search and depth limit search. Thank you.